Hello everyone, this is Mr. McMillan. I'm here with an instructional video. This time it is a continuation of the transformations by performing multiple transformations in sequence, and then it'll also be the symmetry instructional video. So with multiple transformations in sequence, sometimes we'll be asked to do multiple transformations on the same object. So if we want to do that, we have to do them in the order that it wants us to do. So let's look at the first one here. It says perform the following transformations in sequence. And A says xy maps to x plus 9, y minus 3. And the second one says to a rotation 90 degrees counterclockwise about the origin. So here's what you need to do. You're looking first and you're identifying what transformation that you have. So here, when you see the mapping rule here that has x plus 9, y minus 3, that is when you're doing a translation. Okay, that's what's called a translation rule. And if you're adding 9 to the x, you're going to the right 9 units, because right is the positive direction. And you're going down 3 units for your y.
Please contact the front office.
So the first part we need to do is we need to take A, B, C, and D and perform a translation right 9 units, down 3 units. And that's going to be our A prime, B prime, C prime, and D prime. So A, we're going right 9 to here, and then down 3 here. So that's your A prime. I'm not going to connect these. And you'll see why here in a bit. B, you're going to go right 9, down 3. C, you're going to go right 9, down 3. And D, you're going to go right 9, down 3. And those are your points after your translation. Now, when we do a rotation, or when we do our second one here, we're going to be using these new points, these ones in red. So these are going to be the ones that we're going to rotate 90 degrees counterclockwise. Now, if you're using the formula, this would be xy maps to, you change the sign on y, leave x the same, but then you switch the positions. So this would become negative y, comma, x. Okay? So negative y, comma, x. Alternatively, if you have this drawn, you're doing a counterclockwise. Counterclockwise would be 1 to the left, 1 turn to the left, 1 90-degree turn to the left. And then this would be your new coordinate plane. Okay? So for instance, the new coordinate here, you start at the origin, you're going left 4, up 1. So A double prime would be at negative 4, positive 1. So you would plot that point and label it A double prime. All right, then you have B, rotate again, and it is at B double prime would be at 1, positive 3. One positive 3. And then you have C, which would be at negative 2, positive 6. And then here you would have D, which would be at negative 6, positive 6. And these shapes will overlap, but that's okay. And the blue shape is the one that has had both happen to them. And make sure you do it in the correct order by what it says. So if it says do this and this, make sure you do the one that's listed first before you begin doing anything else. Okay? So let's look at number 2. And number 2, you can try it on your own if you want, but number 2 says perform a reflection about the x-axis and a reflection about the y-axis in that order. So here, I'm going to do this all in one fell swoop since there are 2 reflections and they're over the axis. So I'm going to start with S, and we're going to reflect it over the x-axis first. So remember, when you're reflecting over the x-axis, you're counting the spaces that S is away and then counting in the opposite direction that same number of spaces. So S is 2 below the x-axis, so S prime would be 2 above. Well, so now you're here, now you're here. Now you're going to do a reflection about the y-axis. So you're 2 spaces to the left of the y-axis, 2 spaces to the left of the y-axis, and you need to be, when you do your reflection, you would be 2 spaces to the right. So that would be where S double prime would be after you do both of them. Then you do R the same way, reflect it over the x-axis first. So it's 7 below, so it needs to be 7 above. And then it's 8 to the right of the y-axis, so it needs to be 8 to the left of the y-axis. So your R prime would be here. And then finally T is 5 above the x-axis, so it needs to be 5 below the x-axis. And then it's 4 to the right of the y-axis, so it needs to be 4 to the left once you do both of them. And then that gives you T prime there, connect. And this is your reflection or your transformation done with both reflections simultaneously. So this would be your final answer. Now on some of these problems, it will ask you to do one of these multiple transformations, and it may just ask you for one of the coordinates. So the same deal applies. You just make sure that you choose the correct point and then perform the transformations on it. So now let's get into symmetry. Okay. So with symmetry, there are 3 different types of symmetry, and from previous classes you've probably learned about line symmetry. And a figure is said to have line symmetry if there exists a line such that the 2 halves of the object created are an exact match or reflection, whichever way that you want to say. Okay. And a figure may have 1 or more lines of symmetry. So for instance, take a rectangle. So any type of rectangle, say this piece of paper, but I'm going to draw a rectangle just to show you. If you take this rectangle and you fold it in half, say you fold it in half like this, would that be a line of symmetry? And the answer is yes. Obviously, if you fold the paper, the corners would meet exactly, and there's an equal number to the left and the right. Well, what if you did it here? You did it the opposite way. So instead of folding it from left to right, you fold it up and down. Would that be a line of symmetry? And the answer is yes again. So we know it has at least 2. So now we're going to look at the diagonals. So let's take the diagonal for instance. Now you may say, hey, that has an exact, the exact same amount on the left and the right. So obviously that's a line of symmetry. But say we take a piece of paper in a rectangle, and all I have is this bag, or this little thing out of the bag. And I try and fold this on the diagonal, okay? So I try to fold this on the diagonal. If I try to fold it across the diagonal, like this, are those 2 ever going to meet up? This corner would have to meet up with this corner, but obviously this corner is going to be sticking over here. And there's not an exact match across that diagonal. So the diagonal for a rectangle does not work. So for a rectangle only has 2 lines of symmetry. If you also look at an equilateral triangle would have 3. And the reason an equilateral would have 3 is because you could split it down the middle, and then you can do that for each of the vertices, and you have 3 vertices because all of the sides are equal. Now, if you were doing an isosceles triangle instead, an isosceles triangle would only have 1. So for instance, if you had like this, that's not an equilateral one. It is isosceles, so that line there would be your symmetry, but it wouldn't have any other symmetry at all. Okay. So the line of symmetry is also called the axis of symmetry. So axis or line of symmetry, you may see either one of those. And some figures have a finite number of lines of symmetry, and some figures have an infinite number of lines of symmetry. So a finite number just means it can be counted with integers or whatever else. So for example, a rectangle and equilateral triangle have finite numbers of lines of symmetry. Can you think of a shape that would have an infinite number? Well, think about how you would divide something. Say, for instance, you had a round object like a circle, right? If you have a circle would have an infinite number of lines of symmetry because all you have to do is fold across the diagonal. But you can do that in an infinite number of ways. You can do it here, 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 all the way around the circle, and there is no end to the number of lines of symmetry because you can always get smaller and smaller and smaller in your precision. So a circle or another round object, say a sphere, would have infinite numbers of lines of symmetry. Okay, something like a rectangle or square or something like that would only have as many as you could count. So make sure that you pay attention to that. Also make sure you pay attention to color. So color can also change things. If a object has patterns in it and some things are shaded differently or some patterns are different than the others, then that can affect symmetry. So for instance, if you take a square normally has 4 lines of symmetry, the 2 diagonals, then the vertical and horizontal. But let's say you split this into 4 quadrants. Okay, 4 equal quadrants. And you color the top left one and the bottom right one blue. And you leave the other ones white. Or you could change them to any color other than blue. Okay, so imagine those are completely colored in. Now, if I draw my vertical bit here and I fold it across that line, are these symmetrical? Well, if it were a normal square without these quadrants, I would say yes. But because they are not the same color when you fold them across, they don't match up exactly. So that means that this would not be symmetrical even though the normal square would be. And the same thing would apply for this type of line of symmetry. That one wouldn't work. But this one would, and the other diagonal would. So the 2 diagonals would work, but the other ones wouldn't. So because of the color, the shading, that can change things. So just make sure you're aware of that. Okay. The next one, a point or figure is said to have point symmetry if the figure looks identical when rotated 180 degrees. And what it means by that is that it overlaps with the original figure exactly. Okay, so this means the figure looks the same upside down as it does originally, And if a figure has point symmetry, then it must also have rotational symmetry. So for instance, some things that have point symmetry, a rectangle would have point symmetry. You could rotate this 180 degrees, flip it upside down, and it would still look exactly the same. A square would look exactly the same. A circle would look exactly the same. Even this square with the colored in circles would, or squares would. Okay, but something that wouldn't would be something like a triangle or a pentagon, you know, or something like that. Typically, things that have an odd number of vertices are not going to be able to have point symmetry because they are not rotated, or when rotated 180 degrees, they have like a point. So for instance, if you rotated this triangle here 180 degrees, this is what it would look like. And that is not the same as that. Okay. All right, and the last bit here, rotational symmetry. I just throw this in just in case you ever do see it. But the line symmetry and point symmetry is what we're worried about. A figure is said to have rotational symmetry if the figure can be rotated less than 360 degrees and the rotated figure matches the original figure exactly. So just like point symmetry where it has to be rotated 180 degrees and look exactly the same, that would also have rotational symmetry if you manage to do that. The minimum value of the order of rotation, which is how many times it can be rotated before 360, is 2. A value of the rotation, order of rotation of 1 would only be 360, which would not have rotational symmetry. So this means that the figure will be the same when rotated 180 degrees. Now the order of rotation is going to rely on the number of times it is identical to the original figure before a rotation of 360 degrees. For instance, consider a square. What would be the order of rotation of a square? Well, if you take a square, how many degrees would you have to rotate that in order for it to look identical? Well, you would only have to rotate this 90 degrees to make it look identical. So that's 1. Okay, well, you could rotate it another 90 degrees, which is a total of 180, so that's 2. And then you could do another 90 degrees, that's 3, and then you could do another 90 degrees to get back to 360, and that's 4. So the order of rotation would be 4 for a square. For something like a rectangle, it would be 2. Something like a hexagon, it would be 6, and so on and so forth. It just depends on how many times it matches up exactly. Now the minimum angle for the figure to match exactly is called the angle of rotation. So for a square, that would be 90 degrees. And this angle will always be a factor of 360 degrees. So that means that the shape, when rotated, the angle will always divide evenly into 360. So for example, 90 goes into 360 4 times, 180 goes into 360 twice. So you could have something that has 40 degrees or 10 degrees or whatever else. You couldn't have something that goes in like 50 degrees. There's not going to be anything that rotates 50 degrees and matches up exactly because it's not a factor of 360. And that's going to do it for this video, guys. I hope this video was helpful. Make sure that you remember for the worksheet that an x equals a number is a vertical line. So x equals 2, 7, anything like that. And a y equals a number is a horizontal line. Okay. That's going to be very helpful when you're trying to figure out symmetry. Thanks, guys, and I will see you in the next video.